Hi, in this lecture, we're going to deal with the differential pair, which is a very important example being covered in the CMOS book from Dr. Jacob Baker in chapter 9. The CMOS. And you can find all these equations and derivations in chapter 9 of the book. Okay, and in this example, you are going to be trained with how to deal with all these DC and AC analysis with the integrated circuits, how to find out if the CMOS transistor is being operated in triode or in saturation region. Okay, so let's start working on that. So the differential pair. I'm going to draw the schematic first, and we are going to do the DC analysis for this lecture and do AC analysis in the next lecture. So the circuit looks like this. I'm going to draw it probably on the side, so I have space to do the calculation here. Nice. Go up. Ground this guy. They are 5 volts VD. And these two transistors, and there's a current source is drawing current 40 microamps current to the two channels. And this transistor has a AC input. I shouldn't do that. And a DC input as well. It's 2.5 volts, and this is 1 millivolts. And the same here, it's 2.5 volts. Should make it clear. So that's a circuit. And the first step is what we need to do is we need to make a DC analysis to find out all these voltages at every node. Here, like here, and even here. So you're thinking about, so there's a current source. How can I know the DC voltage here? Okay. Yeah, so let's start running the calculation. In this video, we're going to do a DC operating point analysis. Okay, so the first step, so look at the two DC voltages. And because this is 40 microamps, it's going to draw current to the two branches, and they are going to merge as it's joined, and totally have a 40 microamps current flow to the ground. Because they have all these two transistors has the same VGS. See, so because they are shorted at the S terminal, and also they have the same G for DC, which is 2.5 volts. So for each branch, it will be equally 20 microamps. So the first step, you want to say, and I forgot to label them. So that's M1, that's M2, M3, M4. So for the first step, M1, M2 have the same VGS. So they have the same ID equals to 40 microamps divided by 2, which is 20 microamps. So that's the first step. You want to be clear for this point. Okay. And the second one, if we know ID, right? So that's 20 microamps is the ID for this transistor and this transistor and also this and this. Okay, if you know ID, can you still remember that the equation I want to use to calculate VGS? Remember that one? VGS equals to 2ID over beta n plus VTHN. So this is from the square law equation. If you forgot how we get here, just look at the notes from the last lecture. Okay, I have all the derivations over there. So that's a VGS. And ID equals to 20 microamps. It's going to be 2 times 20 microamps over beta. Since we're going to use beta n all the time, so let's just do a calculation. So what is beta n? Beta n equals to 120, so this is from the model, microamps per voltage square over, I keep doing that. There's nothing over anything, okay? And the dimension, I forgot to put it here. So for all the NMOSes, they are 10 to 2, and for PMOS, they are 30 over 2. Okay, so this is given. And beta n equals to this one times 10 over 2, which is 600. Right, so this times 5 will be 600 microamps per voltage square. So if we know that, we just plug in beta n over here, 600 microamps per voltage square, and plus VTHN. So what is this? 40 over this plus 0.8. So VTHN is 0.8, right? So let's do a calculation real quick. So that's 40 over 600 and square. So 0.26. It's going to be 0.26 plus 0.8, which is something around 1.06 volts. Okay, so that's VGS. If we know VGS, we can calculate VS because that's a terminal S over here being shared by these two NMOS transistors. We know VGS. We know VG, right? We know VG, we know VGS. So what is VS? Because VGS equals to VG minus VS. So VS equals to VG minus VGS, right? And VG is 2.5 volts. Keep in mind, so 2.5 volts over here is not VGS, it's VG only because VS is not grounded. They're not sharing the same ground, right? Ground is over here. This point is unknown. We have to calculate it. So this point is VS compared to the ground. So VG minus VGS will be 2.5 volts minus 1.06 volts, which is actually 1.44 volts. Okay, so that's VS. That's the voltage at this point. Okay, so that's the second step to calculate VS. What's the next one? Since we know VS right now, so we know VG, we know VS, but we don't know this, we don't know this, right? So now let's do it one by one. So let's get this one first. So what is that one? Should be because this is a diode connection, so we know that this PMOS is going to be operating in the saturation region, and we know VS over here is no, we don't know this yet, but we know 20 microamps. So the same concept. So for the third step, we are going to calculate VSG3, okay, which is a voltage from VS to VG, VS to VG. So VSG3 equals to same concept, same equation, beta P, right, and plus VTHP. This is 2 times 20 microamps over beta P. So what is beta P? Let's calculate it. Beta P is 40 from the model, right? 40 microamps per voltage square times. So the PMOS is 30 over 2. So it's going to be 15 times 40. So it's still the same number, just by chance, right? I didn't produce design by the number designed in the textbook. So there, it's getting the same number here. So it's make the calculation a little bit easier. So what is this? Because the threshold voltage for the PMOS right now is 0.9 volts in the model file, but we know this one is the same value. It's going to be 0.26. Just copy it over here, plus 0.9, which is 1.16 volts. Okay, a little bit higher. So that's VSG. That's VSG. We know VSG here, right? Plus minus VS, so that's VSG. And we know 5 volts, we know VS. So we can definitely get VG. And VG equals to this point, the voltage at this point as well. And this point is going to be VG3, right? So the gate voltage for the M3 transistor. And also the same point, it equals to the drain voltage of the first NMOS transistor of M1. So this equals to VD1, right? So the drain voltage of M1 is the same as the gate voltage of M3. This is being shorted together. Since we know VS, we know VSG, so definitely we can get VG3. So we will know VD1 as well. Okay, so that's the fourth step. If we know VSG3 is this, so we are going to know VG3 equals to VDD, which is 5 volts, minus, let's label that, okay, VDD minus what? Minus VSG. So VDD is actually VS, right? So VDD minus VSG equals to VG3, and this is 5 volts minus 1.16 volts, which is 3.84 volts. Okay, so that's VG3 equals to VD1. Okay, so now we know VD1, we know VS, and now let's take a look. So we can make a judgment about the regions of the operation for these two transistors. So this voltage equals to what? So VD equals to 3.84 volts, we just calculate it, right? And VS equals to 1.44 volts. So what about VDS now? Since when we are trying to find out if this one is operating in which region, we have to find out the VDS and also VGS minus VTH, right? So which is the VDS set. So VD equals to this, VS is equal to this. So VDS is larger than 2.4 something volts, right? So it's 2.4 volts. And this minus VTHN will be 2.5 minus 0.8 volts. Yeah, let's write it down. So VDS1 equals to VD1 minus VS1 equals to VD1 minus VS, which is because VD1 is 3.84 volts minus VS. VS is 1.44 volts. So totally this is 2.4 volts, right? So that's VDS for M1. So what is VDS1 set? Equals to VGS1 minus VTHN, which is 2. What is VGS? VGS is 1.44 volts. No, VS is 1.44 volts. VGS is this 1.06 volts. 1.06 volts minus 0.8 volts, which is 0.26 volts. That's VDS set. It is positive. It is higher than 0, which means the NMOS will be turned on. But the thing is, you can see that your VDS is way larger than VDS set. So definitely, M1 is in saturation. Okay. So what about M3? VSD3 equals to 5 volts minus VD1, which is 5 minus 3.84 volts, which is 1.16 volts. What about VSD3 set? That one equals to VSG3 minus VTHP, which is what is VSG3? VSG equals to VSD, right? Yeah, I know you already see the answer, but let's just do it. Which is V 1.16 volts minus 0.9 volts, which is 0.26 volts. Okay, so that's the overdrive voltage, or you can say this is VSD3 set. So you can definitely tell that VSD3 is larger than VSD3 set. So M3 is in what? In saturation as well. So 2 has been figured out, and we have 2 left. Okay, so these 2 are a bit more difficult, but let's work on this. Because we know that this transistor is pretty interesting because the gate is being shorted to the ground. So which means it's going to be a pretty large VSG drop. Okay, so so the VSG will be 5 volts definitely, no doubt. Okay, so for M4, wait, right now we are at step 6. So for M4, VSG4 equals to 5 volts minus 0 volts, which is 5 volts definitely, and VSG 4 minus VTH P equals to 5 volts minus 0.9 volts, which is 4.1 volts. Okay, it's pretty high because you have to have your VSD, because this is VSD set, right? This is VSD4 set. That's for the PMOS, VSD set voltage for the PMOS. And we have to have a VSD larger than the VSD set to saturate this transistor, this PMOS. The problem is it's pretty hard because you can imagine that if VSD4 is larger than 4.1 volt, which means VS4 minus VD4 has to be larger than 4.1 volts, right? So VS is 5 volts minus VD4 has to be 4.1 volts. So VD4 has to be smaller than 0.9 volts, which means the drain voltage over here has to be smaller than 0.9 volts. So it's going to be a super tiny, super small drain voltage for M2. But we know that very likely M2 is being operated in the saturation region because it has the same BGS and the flowing has the same 20 microamps flowing through M2 compared to M1. So we pretty much know that M2 is being operated in the saturation region. But if you want to make this one saturate, you have to have this voltage to be smaller than 0.9 volts, which will not be able to saturate M2. You know what I mean? Because your VSS is right at 1.44 volts. Okay, how can you have a lower voltage here at your drain node to be lower than the source voltage, and you still have a current flow through the channel from the top to the bottom? It's impossible. Okay, because we know that it's going to be 20 microamps flow from the top to bottom, so the voltage here has to be higher than Vs, which is 1.44 volts. Okay, so this guy cannot be in saturation at all. So the hypothesis at the very beginning saying this is in saturation is wrong. So we cannot let this one to be operating in the saturation region. You know, so it has to be in the trial region. However, so because this has to be smaller than 0.9 volts, however, Vs 2, right? Because this Vs2 here equals to 1.44 volts, and the current flows from top to bottom, which means the voltage drops from VD4 to VS2. So VD4 cannot be smaller than 0.9 volts. So M4 is not in saturation. Okay, here's the conclusion. So if it's not in saturation, it's going to be in trial because you get current flow through the channel, so it cannot be turned off. It won't be off, so it's going to be on. It's on and it's not in saturation. It has to be in trial region. All right, so given that M4 is being operated in the trial region, so we have to use the trial region square law equation to calculate the voltages and currents. We cannot use a regular one for the saturation region. So the equation is ID because it's 20 microamps on the two branches, So this one 20 microamps as well. It's going to be 20 microamps equals to beta P times VSG4 minus VTHP times VSD4. Don't forget this term. Minus VSD4 square over 2. Yeah, you don't need to dig too deep into here. Just remember this equation. And this one equals to 40 microamps per voltage square times 30 over 2, because that's the ratio for the width and length of the PMOS. And VSG4 apparently is 5 volts minus 0.9 volts. It's going to be 4.1 volts times VSD4 minus VSD4 square over 2. So now let's solve for VSD4. It's a quadratic equation. And apparently you can cancel these two terms and get a 2 here left. And 2 get canceled. So it's going to be 30 times 4.1 VSD4 minus VSD4 square over 2. And this will be 1, 2, 3 VSD4 minus 15 times VSD4 square equals to 1. You move everything to this side, you're going to have 15 times VSD4 square minus 1, 2, 3 VSD4 plus 1 equals to 0. So VSD4 equals to 1, 2, 3 plus minus 1, 2, 3 square minus 60. And over 30. Okay. So now there are two possibilities, and now let's take a look which one is more possible. So we have to calculate this first. Anyway, so now let's find out what is that value is. So it is 1, 2, 3 times 1, 2, 3 equals to this, and minus 60 and square root. So it is 1, 2, 3 plus minus 1 to 2.756 over 30. So if VSD4 equals to 1 to 3 plus 1 to 2.756 over 30, it will be 245.75 over 30, which is, it's a pretty large number, right? This is larger than what? Larger than 8 volts. And that's impossible because overall you only have 5 volts for the power supply. How can I get a voltage drop over these two terminals to be 8 volts? It's impossible. So this is impossible, right? Impossible. So VSD4 will be this minus, which is 244 over 30, which is 0.008 1 volt, which is something around 8.1 millivolts. Okay, so now this is final VSD4, and now let's verify if this is right. So since VSD4 is 8.1 millivolts, which means the voltage drop across these two terminals are 8.1 millivolts, tiny. Okay, since when this transistor is being operated in the trial region, VSD is tiny. So VD4 will be VS4 minus VSD4, which is 5 volts minus 8.1 millivolts. It is 4.992 volts. Okay, So you get a pretty large VD, which is a good news because this voltage is high or is higher than Vs, so you can get M2 being operated in the saturation region because VD4 equals to VD2, right? So VDS2 equals to 4.992 volts minus 1.44 volts, which is 3.552 volts. And also you'll know that the DS2 set is only VGS2 minus VTHN, which is 0.26 volts. So apparently this is larger than that. So M2 is in saturation. And M4 is in child. This is how you verify all these DC operating points in this circuit. And in next lecture, we are going to cover the AC analysis for this circuit. So be patient. This circuit covers a lot of stuff. We're going to get this figured out. If you all have any questions, find out just read the chapter 9 of the CMOS book. It's more clear over there, so you can find a lot of details about the calculation. All right, I'm gonna see you in the next video.